Mechanics of Materials, Chapter 5, Torsion, thin walled hollow section versus a solid shaft example. Let's solve an interesting problem in torsion in thin walled sections. So in this example, we do have a solid circular shaft, a solid circular shaft versus a thin walled rectangular cross section with a thickness of T minimum. If the shearing stress in both are equal, we are looking for the thickness of the rectangular thin walled section. So the equation for thin walled section or thin walled hollow section is tau is equal to T over 2 area average times the thickness, which is T minimum in our problem. And we do know the diameter of the solid shaft is D, like the width of our rectangular cross section, and at the same time they do have a tau circle is equal to tau rectangle. So if that's the case, for tau maximum for a solid circular shaft is the formula is Tc over J. Tc is R, which is D over 2, diameter over 2, and a half of pi times R to the 4 or D over 2 to the fourth. And that's make it like tau maximum in solid circular shaft is 16 times torsion over Pd cubed, P times diameter cubed. And on the other hand, tau maximum at the hollow thin walled rectangle is coming from this equation. So that's T over 2 area average times the minimum thickness. And for our case, because T is relatively small to D and 2D, so we can just consider it's almost A average is D times 2D squared. So that's 2D squared. If you plug that back into AM, then you can have like tau maximum for hollow thin walled rectangular section is T over 4 times D squared times T minimum. And if based off problem statement, tau max in circle is tau max in rectangle, so it just says 16 times torsion over Pd cubed, and these two T are identical. We just have it like parametric. Pd cubed is equal to T over 4 a D squared T minimum. So if we cancel out T with each other, and then we can have a T minimum like P times diameter over 6D4. Thank you. We'll solve more problems.